Welcome everyone. This video talks about projection planes and specifically about circles. So for starters here we have a part that is sitting on a fixture plate. Looks like the part is nice and square to that fixture plate. So if we were to, let's say, go to the top view and then measure this circle on the CMM, basically we would touch probably 4 points on this circle. 1, 2, 3, and 4. They would be at the 3, 6, 9, and 12 o'clock position. And after measuring that profile, we would get something that looks like this. I'll turn off the visibility of the fixture and temporarily turn off the visibility of the part. And there you can see the profile that we would get by measuring this part. So if I right-click and analyze entity properties here, I see that that diameter is 375 thousandths. I turn on the part, and I'll analyze entity properties, measure the part itself, and sure enough, that diameter says 375 thousandths as well. So this is kind of common sense. We know that all measurements in metrology should be square. If our part is nice and square to the fixture plate, everything comes out correctly. But we know in this world, things are not always perfectly square. So I'm looking over at the M-Cosmos training manual here. I'm looking at page 34, and this has a quick excerpt on this. It says that if your part is perfectly square to the granite, then the plane that you're measuring in will be perpendicular to your primary datum, which is exactly what you want, and you won't get measurements that are skewed. Now, in the real world, we know that this is not always the case. We know that our parts are not sitting perfectly square on the machine, or perhaps the parts themselves are not exactly parallel from the top surface to the bottom surface. So they will sit a bit skewed. This is why we have alignments. Alignments compensate for the fact that the top surface that you're measuring from, which is usually your primary datum, it might not be level to the machine, and it can digitally rotate the coordinate system to do that. So the alignment is the primary method of how the machine accomplishes that, and then from there it uses projection planes to either project features onto the top surface, the front surface, or the right surface from there, and that helps the software take measurements. So this book leaves a little bit to be desired on that topic. I think this is a great summary, but let's go a bit more into detail. So let's pretend that our part is not sitting nice and square. We saw everything works easily when it is square, but let's pretend that we have a part that is sitting on an angle. And why is it sitting on an angle? Well, you can see I've simulated here. We have a little metal chip underneath the part. So this can happen, you know, we work in a shop environment. Perhaps you're working on a CMM that's out on the shop floor. Machines are cutting metal chips off of parts. Sometimes they fly out of the machine and land on the fixture. So if you have, you know, an operator who's maybe not as experienced, they may not wipe down the fixture plate before they put the part on. And now we end up in this scenario. So the issue here is that the part is not sitting flush to the fixture. And really, that plane right there shown in orange is where the machine's primary datum is. So if you move just the X or the Y axis of the machine, it will move along this plane, right? That would be the X axis. This would be the Y axis. The problem is the top surface of the part is not along those axes because the part is sitting off kilter. So if we took a profile of this part at this angle, turn on a level that shows the profile is shown in white here. And I'm also going to turn off the fixture's visibility, and I'll turn off, well, we will look at the top view so that you can see that this profile does indeed line up with the part. Turn on our translucency toggle, you can see that it lines up nicely. And now we'll turn off the visibility of the part in that angled plane, so that way we can see what we're working with here. So if we measure the profile without doing an alignment, and we try to project that circle up onto the plane, this is what we'll end up with. If we look at the circle through Analyze Entity Properties, we see that it's not actually a circle at all. I used the silhouette boundary command in Mastercam to create this, and that command takes its best representation of what the profile looks like. And in this case, yeah, it says it's 373 thousandths in diameter right here, but if we measure the next segment, that's 378 thousandths. The next segment is 353 thousandths. So we're getting a pretty wide discrepancy in what this circle looks like. And I guess the bottom line is, without projecting this perfectly onto our primary datum, it's not a circle at all. It's an ellipse. So how do we even find out where the center is? Well, In Mastercam, I drew a line from the 3 o'clock position over to the 9 o'clock position, from 12 o'clock down to 6, and that gives us our intersection here. Now, if we compare that to the original profile, notice that the original profile is shown in green and the new profile is shown in white. Those center points do not line up, right? One is shifted off from the other, and the reason for that is this plane is skewed. The part is not sitting square on the fixture. Well, let's say we want to take some measurements from this. What does the CMM software do to turn this angled profile that's really a bunch of individual segments? How does it turn that into a circle? So this will give you a little bit of appreciation for the CMM software. I know it's sometimes difficult to use. It's not the most intuitive piece of software, but it's doing a lot for you in the background. So here is the basics of how the CMM software is turning this broken up profile into an actual circle that we can output measurements for. So the first thing it does, it looks at the intersection between the data that we've collected and the center point, and it creates points here. I'll turn off the center point so we can see that those points intersect at the 12, 6, 9, and 3 o'clock position. Okay, next thing it does is looks at the fullest extent, the biggest distance in between any 2 points, and in this case, that biggest distance is the distance from the 12 o'clock position to the 3 o'clock position. So shown in red here is the high limit of the circle. We'll say this is the biggest circle, or the enveloping circle. Then it looks at the closest to distance between points, and in this case, that's drawn in light blue here. That is between the 9 o'clock position and the 3 o'clock position. You can see there is a slight gap on the top and the bottom, and we would call this the inscribed circle, or the lowest diameter of the circle. Now, here we have two options. So if we analyze entity properties, we see the biggest circle is 375 thousandths, and the smallest circle is 362 thousandths. And there's a pretty wide discrepancy there. So which one do we use? The CMM only outputs one answer in the tolerance dialog. So it will come in here and create a best fit circle. And we'll talk a little bit more about this when we get to the fitting algorithms. That will come in a separate video. But the basic idea here is you take the lowest point on one circle and the highest point on the other circle. Here I've represented that with this green line that connects the lowest point on the blue circle to the highest point on the red circle. And now I'll turn off the small circle and the big circle just for clarity. And here we can see our best fit circle. So our best fit circle is halfway between the inscribed circle and the circumscribed circle. And this is essentially the average of those two circles. So if we analyze the entity properties and measure this, we see that that comes out to be 369 thousandths. So I guess the bottom line is, if we compare the square profile, shown in green here, to the adjusted profile that we just came up with, the adjusted profile gave us 362 thousandths. The original profile, shown here, gave us 375 thousandths. So without projection planes, we essentially measure features that are the wrong size. The whole idea of an alignment is to square up the part to the machine. Even if it's not mechanically square to the machine, an alignment will skew it so that it's square enough that the machine can take measurements. And projection planes allow us to take measurements off the part and then project them onto the alignment. That turns features that are not actually perfect circles into perfect circles, so that way we can tolerance them. All right, thank you for watching. I'll see you at the next video.